Hello everyone, welcome to Module 9. We'll talk about correlation analyses in Module 9. So there are a variety of types of correlations. We're going to talk mostly about Pearson's correlation, and I'll talk a little bit about partial correlations at the end of the lecture. I'll talk a little bit about Spearman's row and Kendall's tau and point by serial at the end of the lecture as well, but I won't spend a ton of time on these because once you know the basic idea of correlation, you'll be able to run all of those analyses. This is actually a pretty simple analysis, especially as we're coming off of factorial ANOVA. So I think you'll find this one refreshing and easy and lovely. Okay, so the basic logic of Pearson's correlation, which we'll talk about first. Correlation analyses indicate the association between two continuous interval or ratio level variables. And regardless of the type of correlation, that basic logic is still the same. Correlation analyses indicate an association between two variables. The different kinds of correlations address different kinds of variables. So in Pearson's correlation, we're talking about two continuous variables measured on an interval or ratio scale. And the correlation analyses will indicate to us the statistical significance of the association, the strength of the association, and the direction of the association. And I'll tell you more about this in just a second. Correlations allow us to see basically if two variables move in the same direction. And so you'll hear people say variables are negatively correlated or negatively associated and positively correlated. Negative association or correlation means that as one variable increases, the other one decreases. So they're moving in opposite directions. In a positive correlation, as one variable increases, the other one also increases. So they're moving in the same direction. Correlation values range from -1 to +1. 0 indicates that there's no relationship at all. And there are some markers for what we consider sort of weak, moderate, or strong relationships. And to get an effect size for this particular analysis, it's very easy. All we have to do is square the correlation value that we get. So the correlation value that we get is represented as an R. And if we just square that R value, we get an R squared, which is why it's called an R squared. And then we can interpret that R squared using the standard Cohen's effect size evaluations to evaluate effect size. And we've talked a little bit about those before, and those are pretty easily found online. And I believe they're in your textbook as well. So there are a variety of kinds of questions that we might ask that can be answered by correlation analyses. So one of the ones that you'll see online a lot, this obviously has nothing to do with sexuality, but one of the ones that you'll see online a lot is are SAT scores associated with college GPA. A lot of people use that particular example because you'll see some very pretty correlations in terms of strong associations between SAT scores and college GPA. Some questions that are more appropriate for us in nature is there an association between sexual satisfaction and relationship satisfaction? And we might hypothesize here that there would be a positive correlation such that as sexual satisfaction increases, relationship satisfaction also increases. And we could look at that the other way, and we say that the other way too. As relationship satisfaction increases, so does sexual satisfaction, it also increases. We could also ask, is self-esteem associated with contraceptive self-efficacy? Which, as you've probably guessed from the course of the lectures so far, we'll analyze that question today. So there are some assumptions of the Pearson's correlation, just like there are assumptions of any of the analyses that we're talking about. We talked a bit in the beginning of the semester about removing outliers. This is an association in which outliers can have an influence, and so we want to try and really think about those outliers and remove them, or try and minimize them, or find out if they're influential in some important way that we might need to think about getting rid of those people or their data. We also want to know that there are linear relationships between the variables, so that there is essentially a straight line relationship between the variables. I think I've talked a little bit before about curvilinear relationships, which when we create a scatter plot would look like a U or a smiley face, for example. And that would be a situation in which if you're looking at the x-axis and you have one variable, that the scores on the other variable might be, let's say, high at low ends of your predictor variable, low at the middle range of your predictor variable, and then high again at the high range. And I'll show you an example of what I mean, or use a graph to show you a better example of that. Much like most of our analyses that we've talked about before, we want to know that our variables are normally distributed. And again, much with the same as many of our other analyses that we've looked at, we want to know that there is homogeneity of variance, or homoscedasticity, as it's called. And that's equal variance of the variables at all levels of the other variable. And I'll show you a little bit about how we try and evaluate that. So one of the main ways that we evaluate most of these assumptions is by looking at scatter plots. I think we've looked at these once before, though I don't recall. Scatter plots essentially illustrate the association between two continuous variables. They can do other stuff too, but we'll look at them in terms of looking at the associations between two continuous variables. Scatter plots have two dimensions, much like all plots or graphs. They have the x variable, which we think of as the independent or predictor variable, is arrayed along the horizontal or x-axis. And the y, the dependent outcome variable, is arrayed along the vertical or y-axis. The interesting thing about correlation analyses is that in some situations you may have a variable that you're thinking about as a predictor variable, and another variable that you're thinking about as an outcome variable. But correlation analyses rely less on thinking of one as a predictor and the other as an outcome variable. We may just want to know the association between two kinds of variables. We'll often think about them as predictors or outcomes in most of our analyses, but we may just be looking at associations without necessarily thinking about one as being predictive of the other. And so each dot on a scatter plot is a case, is a person. And the dot is placed at the intersection of that case's scores on x and y. I'll show you a picture of this in a second. And in most scatter plots, what we want to do is try and fit a regression line. And we'll learn more about regression in Module 10. I'll give you a little sort of brief intro to help you understand the regression line. The regression line is a single straight line that comes as close as possible to all of our data points. And it indicates the strength and the direction of the association between the two variables. And so the greater the extent to which the dots are clustered along that regression line, the stronger the association. And again, this will make more sense once you see a picture. So the regression line formula, this will make a little bit more sense when we talk about regression in Module 10, is y equals a plus bx, where y is the score on the dependent or outcome variable. It's what we're trying to predict usually. When we think about regression, correlation analyses, so many of our analyses, we're trying to predict some outcome variable. We want to try and understand what's going on and make better predictions about the world. And so we're trying to often predict this y variable, this outcome variable. A is the y-intercept, which is also the point where the regression line crosses the y-axis. So it's the value of y when x is 0. B is the slope of the regression line, which is defined as the amount of change produced in y by a unit change in x. And I'll give you an example of all this in just a second, so hopefully it will make more sense. And x is our score on the independent or predictor variable, or whatever is the other variable from y that we're talking about. And so the best fitting line, regression line, is the one that has the least amount of error. We want to do the best job that we can predicting our outcome variable. So the least amount of error is also called residual. So we want to minimize the distances between the predicted and the actual values. We want to make the best prediction that we can. So I'll show you an example of all this in just a second as we go through the conducting and interpreting correlation analyses. So using the same four-step process, we state the null and alternative hypotheses. The null hypothesis is that our correlation, this is represented as rho, this is a Greek symbol, rho equals 0, so there's no correlation, and all alternative hypothesis is that rho is not equal to 0. So it's either greater than or less than 0. This is a non-directional hypothesis, so we're just saying it's not equal to 0. We want to make sure we meet the test assumptions, as always, calculate the test statistic, and make a decision and interpret the results. So let's talk about making the assumptions and meeting the test requirements a little bit. We obviously state the null and alternative hypotheses. So if we're using Pearson's correlation, we want to make sure that the level of measurement is interval or ratio, so continuous on both our independent and dependent variables, so both x and y. We want to make sure that we have normal distributions or close to it on both variables. There's a little bit of wiggle room in here, but the great thing about correlation analyses is that we have some non-parametric examples of correlation analyses that we can use if our data are not normally distributed. We want to check and make sure that the relationship between the two variables, again, is linear. And we want to check for homogeneity of variance or homoscedasticity. We calculate the test statistic. I'm not going to spend a ton of time on this particular formula. I think your book does a nice job of breaking it down a little bit and helping you think about what this formula contains and how it works a bit. But thankfully we'll just use SPSS. And the important part is that we know when to use the correlation and that we can interpret the correlation. Our degrees of freedom is n minus 2. We're estimating two numbers here, our population mean for x and our population mean for y. And then we make our decisions. We look at the p-value, we look at the strength and the direction of the association, and we evaluate clinical and practical significance. So let's run through a full example, and I'll show you some scatter plots in here as well. And so hopefully a lot of these ideas will come together. So, not surprisingly, the question that we will answer is there an association between self-esteem and contraceptive self-efficacy? So this is using the AdHealth data set. This is sticking with that contraceptive self-efficacy variable that we've been looking at the whole semester. And this is using the self-esteem variable. And so this is, I talked a little bit last time about creating this variable. And we did actually this analysis last time, but we didn't spend a ton of time on it. So I'm going to flesh that out for you. And we'll look at that particular association as its own research question. The null hypothesis is that there is not a statistically significant association between self-esteem and contraceptive self-efficacy. The alternative hypothesis is that there is a statistically significant association between self-esteem and contraceptive self-efficacy. So we'll check that the assumptions of the Pearson's correlation are met, so that our levels of measurement are appropriate. We have two continuous interval or ratio level variables, and that's again for the Pearson's R. We'll check to see that we have a linear relationship and that we have homogeneity of variance. And that we have an approximately normal distribution on both variables. And so as we've done before, we've looked at contraceptive self-efficacy several times, and we've said, meh, but we have a large sample, so we won't worry about it so much. We see roughly the same thing when we look at self-esteem. I'll show you that in just a second. And then I'll show you how to evaluate for the linearity of the relationship and a little bit about homogeneity of variance. So the way that we look at many of these things is looking at a scatter plot. So this is what that scatter plot looks like. This is the instructions for getting this scatter plot. So you go up to Graphs, Legacy Dialogs, choose Scatter Dot, choose Simple Scatter, put your variables into the X and Y axes and hit OK. And then we'll edit the chart to add this fit line, this regression fit line. And so I'll actually go ahead and show you what that looks like right now. So let me pull up this AdHealth data set. So I've moved things around in my AdHealth data set a little bit. Obviously, you are free to move things around, to delete variables that you're not using. So I've put the self-esteem and contraceptive self-efficacy scores up here. So to get this scatter plot, I go up to Graph, go to Legacy Dialogs, and then go over here and choose Scatter Dot. And then I want to choose Simple Scatter right here and Define. And I already have these variables in here, but I'll reset this to see what this looks like. So we can, again, think about what we're thinking about as our X and Y variables. We're trying to think about predicting contraceptive self-efficacy. So let's think about this as our Y-axis variable. And let's put self-esteem in here as our X-axis variable. And so we don't have to put anything else. We can add titles if we want, but we can do that later on as well. So let's just hit OK for now. Okay, so this is what it looks like. And we can kind of see here maybe a hint of a linear relationship. You may not, because this may be the first time you've ever looked at a scatter plot. But what we're seeing here is that these scores tend to cluster down here a little bit in this range. And so again, what each of these circles represents is a single person's score on each of these variables. So for example, if we're looking along here, self-esteem, looks like this person maybe is at a 6 on self-esteem and maybe at like a 4 on contraceptive self-efficacy. And so every dot here represents a single case, and it is their score on both the X and the Y axes, or the each of those variables. And so what we can do here is double click on this, and then we can do a whole lot of stuff in here to try and get a better look at this. So the first thing that we'll do is we'll add a fit line. So we'll add this fit line. It gives us a range of kinds of fit lines that we can add. This is a little bit more what a quadratic relationship would look like, or some of these curvilinear relationships would look like. There's a variety of different options we can have here in terms of variables that we put in, the way that we look at those variables. But for right now, let's just do the fit line right here, and then let's choose linear. And we can attach the label to that line or not, but for right now, let's just leave everything as is and hit apply, and then close. And it already did that for us. So we now have this line that gives us a sense of what that relationship is looking like. And indeed, it is looking like it's fairly linear here. Again, I know that can be hard to look at. I think one of the issues is sometimes that when we look online or when we look in textbooks, they show us really perfect linear relationships and really strong correlations. And those strong correlations just aren't what we typically see in real life. So this is something closer to what we're going to see in real life. I'll show you a couple more examples that are a little bit stronger of a relationship than these two variables, that might give you a slightly better sense of what a strong correlation looks like. Okay, so for right now, let's just let's close this out. This is we can look at a variety of things in this, and we can look at it here or in the other view. So here we can look at the linearities I mentioned. One of the ways that which we can look at homoscedasticity is by looking at how much these scores vary from this line, from this fit line. And what we're looking for here is that it looks like at every level of this self-esteem variable, so all the way down here, all the way up here, that there is a similar level of spread of all of these dots. So what we wouldn't want to see is that the dots down here are all very, very tight to the line, whereas the dots over here get much wider and much farther dispersed, because what that would mean is that the variability in our scores on this contraceptive self-efficacy variable are different at higher self-esteem scores than they are at lower self-esteem scores. And what we see here is it's pretty even. It's a little tough to tell in some ways, because what we see is that there are fewer scores out here at this high end of self-esteem, because there are fewer people who are at this more extreme end of self-esteem. So that's one of the ways that we can evaluate homogeneity of variance, or homoscedasticity. Another thing that we can look at here is seeing about outliers. So on here we can see if there are people who are way far out on self-esteem, or way far up or down on contraceptive self-efficacy. Because both of these scores have a fairly limited range, we don't have to think quite as much about outliers on here. We can look at these self-esteem outliers over here. There are a couple of people who have particularly high scores, and so we can look at these folks a little bit and get a better sense of who they are. So for example, if we click on this person, and I think if you go here and you right click on there, you can actually go to the case and it'll take you back to your data set. And this is the person who has that particular score. So we could always look at that person and say like, is there anything weird about them? Have they said anything specific that we might think about them differently? Can we analyze them in some other ways? We would go back to thinking about some of the ways in which we would analyze outliers on there. We can also sort this self-esteem variable. And so what we see is we have 2 people up here at 26 or at 28, but they're not so far from the people at 26. And because this scale has a top and bottom to it, we're not as worried about outliers on here because it does represent the full possibility of the scale. Sometimes when we worry about outliers are on variables that are count variables. So for example, the number of sexual partners is one that we get outliers on a lot. Most people are probably in the low end of number of sexual partners in their lifetime or in last 3 months or whatever you're asking of people. But you'll always have a few people who are very high. In one of the data sets that I've been working with a lot, we have everybody else who's around like 2-3 partners in the last, I believe we ask about 2 months in that data set. And so most people are around 2-3 partners in that data set. And then we have one guy who's had 121 different partners in 60 days. So he's very different than the rest of the data set. And he throws off a lot of our analyses because he has this undue influence with that incredibly high number. And so we have to think about in most of our analyses whether we kick him out or not. So if we go back to this scatter plot here, that can help us look at outliers, it can help us look at linearity, and it can help us look at homogeneity of variance. So we can do a lot of things here. We can also edit in here and change the labels if we want to. We can type in there. And this is true for any of your graphs if you want to change things and type different things, whatever. The regression fit line, the linear fit line in SPSS, when you do that, it also gives you this equation that I showed you. So this is y equals a. So this is roughly where the regression line hits the y-axis over here. So at 0 self-esteem, the regression line would hit the y-axis. This isn't quite 0 over here, but at 0 self-esteem, the regression line would hit the y-axis. So if it kept going down here, it would hit at like 3.87. And this is the slope. And so what this tells us, what this 0.12 tells us, is for every 1 point increase in self-esteem scores, contraceptive self-efficacy scores go up 0.12 points. So that gives you a really nice sense of how much of an effect one variable has on the other variable. We'll come back to this again to look up at this R squared up here. But for right now, let's just close that out. It saves all that information for us back in our regular output window. So now we can see that in our output window. But for now, let's go back to here. So we can examine our scatter plot and again, check all of our assumptions. So we know our levels of measurement are good. We've confirmed that there is a linear relationship, that there's seems to be homogeneity of variance. What we didn't look at in this scatter plot is the normal distribution on both variables. We've already looked at contraceptive self-efficacy, and you can look at self-esteem on your own. I think I gave you the syntax to create the self-esteem scores, but if I didn't, let me know and I can give that to you. If you remember, we just go over into frequencies under Analyze, and we can put in both of our variables here, our self-esteem total, our contraceptive self-efficacy total, and we can look at our mean, median, our mode, minimum, our maximum, our standard deviation. We can do the skew and kurtosis. And when we want to go in here into charts and get histograms and ask it to show us the normal curve. So now when we get that information, we can look at this distribution. So what we see here on self-esteem, if we look at how close the mean the median and the mode are. They're not terribly far off. They're pretty similar to one another. We can do the calculations to figure out how skewed and how kurtotic this is. But if we go down here and look at this, we see that it actually looks decently normal. It's not terrible. And we've already looked at our contraceptive self-efficacy before, which we've said a sort of similar thing on. It's not terrible, and we have a very large sample size. So let's go with it. So we've examined our scatter plot, we've checked our assumptions, and now let's conduct the test. So this is what this looks like in syntax, and this is what the output's going to look like. And let's move back to SPSS now. So let's go analyze up here, same place we've been going, correlate. For right now, we're just looking at bivariate correlations. So we're going to go into bivariate here, and we're going to put our self-esteem variable and our contraceptive self-efficacy variable. So that's all we have to do. Pearson is already checked for us. That's what we're doing right now. We can come back to Kendall's Tau and to Spearman. We don't have to do any options. We don't have to do any styles. Everything's already checked for us. That's it. Easy peasy. So let's look at what we get here. And let's read this now. So this gives us this little sort of 4-box matrix here. We only need to look in one of the boxes, the one with the numbers in it. So this is self-esteem scores over here, and these are contraceptive self-efficacy scores here. So we want to look at their cross. The reason that you have these ones here is because, of course, self-esteem is perfectly correlated with itself because it's the same variable. So right here, our Pearson correlation, this is our R value. R is 0.176, and it flags this and indicates that it's significant at the level of 0.01. And this is our p-value right here, 0.000. So what we would say is p is less than 0.001 here, so this is highly significant. And this is our n, and I'll show you how to report this in just a second. So we know that our correlation is significant. This is the value of it, and it's a positive correlation. And we already knew that it was going to be a positive association because when we look here at our scatter plot, we see that as this variable increases, moves along this axis here, so this goes from 5 all the way to 30. So as this variable increases, this variable also increases. And this line is moving in this direction. So we know that this is a positive association. As self-esteem increases, contraceptive self-efficacy increases. And we'll come back to interpreting that in just a second. So we have our correlation analysis. So let's come back here. We've conducted our analysis, and we want to make a decision and interpret those results. So this is how we report the R value. So we have a little r, it's italicized. This is our n here, 3719. We have our R value, 0.176, and then we have our P value. Again, P is italicized. It's less than 0.001 because what it tells us is 0.000. So we want to reject our null hypothesis. And we would report this like this, or something like this. Contraceptive self-efficacy scores range from 3 to 15, mean and standard deviation, with higher scores indicating lower levels of self-efficacy. So this is where it's going to get a little confusing. Self-esteem scores range from 6 to 28. Again, we have our mean and standard deviation there, with higher scores indicating lower levels of self-esteem. So both of these are reversed in the way that they're coded. So higher scores indicate lower levels of self-efficacy. Higher scores of self-esteem indicate lower levels of self-esteem. Pearson's correlation analysis indicated that there is a significant positive association between self-esteem and contraceptive self-efficacy, and then we report that statistic. As self-esteem scores increase, contraceptive self-efficacy scores also increase. The R-squared is 0.031, indicating that 3.1% of the variance in contraceptive self-efficacy scores can be explained by self-esteem scores. So this is often how we interpret the effect size here. So this is a really simple one. We just take 0.176 times 0.176, and we get 0.031, and we multiply that by 100 to determine the percent of the variance in one variable that's explained by the other variable. And if we look back to the scatter plot actually gives us this linear r squared up here. So it tells us already what that r squared value is. So when we go to interpret this one, we'd have to think a little bit about what this means. So essentially what it means is that as self-esteem, because we have to reverse sort of the direction of these, it still basically means the same thing. We just have to interpret that in the other way. So we have to think about whether that's important. And we use the effect size, we use what we know about the variable to think about whether or not that's an important amount of the variance that we think that, that we can account for. So 3.1% is not very much variance. And by most standards, we would count this as a small correlation and a small effect size. So we can still talk about it and talk about what it means, but couch that discussion in an understanding that this is a small effect. It may still be important, but it's small. So we can think about both of those things. So as I mentioned, there are a variety of types of correlations. So there are Pearson correlations, which we just went over, and there are ways to conduct partial Pearson correlations. And what partial correlations do are similar in some ways to what we just learned about in ANCOVA, where we control for the effects of another variable. And so in partial correlations, we hold a confounding or a third variable constant to examine sort of a purified correlation between two different variables. And I'll run through a quick example of that. In Spearman's rho, this is actually a non-parametric correlation analysis. So this is something, a correlation analysis that we would use if our variables are not normally distributed. This correlation analysis can also measure the association between two ordinal variables, where the values on each variable represent rankings, like income perhaps, or education level. If we wanted to look at, some people ask you to report partner number in an ordinal fashion, such that those rankings represent higher numbers of partners. So these are good for non-normally distributed variables. These are good for count variables, which are typically not normally distributed. You often have a lot of zeros in count variables. So the number of partners you've had in the last 2 months, for example, a lot of people may have 0 or 1. And so that's not going to be a normally distributed variable. So Spearman's rho can be a good alternative, and it's interpreted in the exact same way. It's conducted in the exact same way. You saw in the little box where Pearson's was checked. We can check Spearman's rho, and it will do that in the exact same way for us. Kendall's tau is also a non-parametric correlation analysis. And this interpretation is somewhat different in that the score represents a probability that the observed data are in the same order versus the probability that they're not in the same order. So this is, again, for these ordinal categories, these rankings. And there are a couple of different versions of tau, tau B and tau C, and they handle rank ties slightly differently. So if people are tied in their rank on each of the variables, they handle those a little bit differently mathematically. I won't go into that here. And then point biserial correlations are very similar to a t-test. This is a situation in which you have one variable that's interval or ratio, and the other variable is dichotomous and coded as 0, 1. So for example, in the first module assignment that we did, we looked at t-tests, and we looked at mean differences in contraceptive self-efficacy for men, boys and girls, young men and women. And what we did was looked at the mean differences according to those two variables, to that categorical variable. And so what we do here is we would still look at this association between the two variables. We would just look at it in this point biserial correlation. And so I think the t-test is easier for most people to understand, but there are certain situations in which you could use a point biserial correlation rather than a t-test. So those are the examples of other kinds of correlation. I'll run you through a partial correlation fairly quickly. And I also showed you a couple more scatter plots to show you a couple of examples of stronger relationships. So as you see here, this R squared linear, this is cut off a little bit, but this is 0.148. So in this situation, 14.8% of the variability in one variable is explained by the other variable. I probably would switch these if I were to do it again, but this is from the Sex and Love data set that you guys have been using for your homework assignments, and this is looking at depression and life satisfaction. So not surprisingly, people who score high in depression are scoring low in satisfaction. So this is an example of a negative correlation or a negative relationship between two variables, such that as depression increases, life satisfaction decreases. And I'll show you how to do this one in just a second. This one, again, maybe not all that surprising of an association. These are the audit scores. So for those of you who've already looked at your assignment for the ANCOVA, the audit is the Alcohol Use Disorders Identification Test. So it's alcohol abuse symptoms, basically. So the higher your scores are, the more abuse symptoms that you're dealing with. And this variable over here is alcohol, drugs, sexual expectancies. This is a big area of my research. This is basically what you believe that alcohol or drugs are going to do to your sex life. So the items on this scale are things like, after drinking or using drugs, I feel sexier. After drinking or using drugs, I'm more likely to be coerced into having sex. So basically how strongly you believe in the effects of alcohol and drugs on your own sexual behavior. So not surprisingly, the more problems you're having with alcohol, the more strongly you believe in those effects. And so what we see here is that 11% of the variability in alcohol and drug sexual expectancies can be explained by alcohol abuse. So again, that's not a terrible effect. It's not terribly strong, but it's not too bad either. And so we see here that for every point increase in the audit total, we see a 1.2 point increase in the beliefs in alcohol or drug sexual expectancies. Again, we have a huge range on this scale here. So we see that people are ranging from 18-ish, I think is what it is, all the way up to 100 over here. And I'll actually run through a quick example for you of looking at some of the outliers in here, just so you can watch me walk through this process a couple more times if that's helpful for you. Okay, so let's minimize this AdHealth data set and then pull up this Sex and Love data set. So I've been giving you guys very small versions of this data set. This is closer to the full data set, not quite the full data set, but this is closer to the full data set. So you can see that there are a lot more variables in here than we've been working with. And so let's look at, let's do the life satisfaction and the depression one again. So let's go through that and let's look at this bivariate correlation. So let's go correlate, bivariate, let's reset this. And so let's look, we have our CESD, which is the depression scale that we used for this. So let's look at depression and then life satisfaction here. So we run just this basic Pearson correlation, and what we see here is that we have a fairly decent correlation. This is negative 0.385, which we already determined that relationship was a negative relationship. And so let's run this scatter plot. Let's go to Legacy Dialogues, scatter dot over here, simple scatter. And so we'll reset this from the last one that I looked at. And so what we're going to look at here, let's think about the depression scores as our x-axis variable, and let's look at life satisfaction as our y-axis variable and run that. So it's just flipping it from what I looked at in the last one, I think. So here we have our depression scores, and here we have life satisfaction over here, and so we can double click on this and let's fit a regression line. Let's close that. And let's actually close that too. So what we see here again is this negative association. So as depression increases, life satisfaction decreases. Again, not terribly surprising, right? The more depressed you are, the less satisfied you feel with your life. And so again, this is our equation that it's using to fit this regression line. So for every point increase in the depression scale, we get a 0.47 reduction, see this negative sign here, in life satisfaction. So that's essentially what that tells us. It tells us that 14.8% of the variability in one variable, we can look at it in either direction. It's the same R squared, so we can talk about that in either direction. But we're going to talk about it as life satisfaction as sort of our outcome variable. So 14% of the variability in life satisfaction can be explained by depression. So that's that example. Let's think about partial correlation. And let's think about looking at what other variables might be playing a role in here. So maybe if we come back to the idea of the audit scores, there's some association we know between depression and alcohol abuse. And alcohol abuse probably also has some association with our life satisfaction over here. So we know that this correlation here between depression and life satisfaction is 0.385, but maybe the alcohol abuse symptoms are mucking this up a little bit. So we want to get a more pure sense of what this relationship looks like. So we want to go up here to analyze, and we want to go to correlate, and then we'll go partial. So here, I already have everything in here, but let's reset that and look at this. So here we want to put these original variables in here. So life satisfaction and depression up here. This is the original correlation we just looked at. And then I want to control for audit scores. So I'll hit OK. And this is giving me the same correlation between life satisfaction and depression scores, but it's controlling for the effects of audit, or holding constant the effects of audit. And so what we see here, our association up here is negative 0.385. Our association down here is negative 0.382. So that didn't have a huge effect. It reduced our correlation a little bit, but it really didn't have all that tremendous of an effect for us. We could look at other variables in here and see what effect they might have. But that gives you a sense of how to do that partial correlation, like what variables you can control for and how you want to conduct that. We can also look at some outliers in these examples and look and see if we wanted to eliminate any of these people and how that might change these things. I won't spend a ton of time on that now because this lecture is getting a little bit long. But what I will show you is a Spearman's row in which we can look at ranks. So I'll show you an example of a pretty obvious one. But some ranked variables that we have in here are education and income. So what might you guess about the association between education and income? You can probably guess that it's a positive association, such that as education increases, income also increases. So what we want to do here is get this Spearman correlation in here. Okay. All right, so what we see here, it gives us this regular Pearson correlation up here, but then it also gives us this non-parametric correlation. And we interpret this exactly the same, but it uses a different formula to arrive at this correlation. So we see that this number is actually different. So 0.422 is what we get for our R value here, whereas in the regular Pearson correlation, we got 0.399. They're still both highly significant associations and very strong positive associations. So there's this is a positive number, so there's a positive association such that as education increases, income increases. We could think about it in the other way: as income increases, education increases. I think it makes more sense to think about it in the first way. And we know that what the strength of this association is in this particular situation. We could get the scatter plot and look at that as well. And we can also calculate our R squared, which would give us a little bit of a better sense and a way to try and explain that. And so if we take 0.422 squared, what we get is about 18, 17.8. So we could say that 17.8 or 18% of the variability in income rankings can be explained by education. So not terrible, a kind of moderate size effect that we're seeing here. So I think that gives you a couple of examples and a couple of ways of walking through that and thinking about interpreting those associations. Compared to some of the other analyses that we've looked at, I think that correlations are fairly straightforward and pretty simple. But again, that's because I know a lot of these analyses already. So let me know if you have questions about this, obviously, if any of it doesn't make sense. For the Module 9 assignment, you'll download the data set and answer the research question proposed in the assignment, just like we always do. Write up a results paragraph. Hopefully that will become a little bit more clear after I put up the example from the Factorial ANOVA that I gave you. APA format again, please, 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 APA format. And as I mentioned in the demo and in the module assignment feedback that I gave you, please make note of my edits to and comments on your previous module assignments and make sure that you've made those in other assignments moving forward. That makes me much, much happier. All right, as usual, if you have questions, thoughts, post those under the general discussion forum. Let me know about them in Google Hangouts. And that's it.